Welcome to the deep dive. We dig into sources, articles, notes, you name it, and really pull out the core insights for you.
Yeah, distilling it down to what matters.
Exactly. And today we're tackling Galileo Galilei. Now, I think most people, they picture the telescope, maybe the trial.
Right, the classic image.
But our sources today, they paint a different picture. His real genius, maybe, wasn't just what he saw, but how he listened, how he understood the universe's motion.
That's it. He's often framed as, the father of modern astronomy, which he was. But our sources really highlight him as a kind of motion decoder.
A motion decoder. I like that.
He was uncovering these fundamental truths about how things move that, well, he didn't know it then, but they really laid the groundwork for this conceptual framework we're exploring today called motion theory.
Okay, and we should probably clarify that right up front. Motion theory, this isn't like Newton's laws, is it? It's more a way of seeing things.
Precisely. It's a conceptual lens. It encourages us to view the universe less as a collection of static objects and more like this dynamic interplay of rhythms, patterns, motion, constantly seeking stability, resolution.
Like seeing the dance, not just the dancers. That makes sense.
Exactly. So our mission today is really to unpack how Galileo shifted thinking by focusing on motion itself, letting it, as the sources say, speak for itself.
And how his discoveries just line up so well with this modern concept of motion.
Right.
So for you listening, think of this as a shortcut, a way to grasp a really fundamental shift in how we see the universe, get some real aha moments beyond just, history dates.
What?
Ready?
Let's do it.
Okay, so Galileo. We think telescope, but you're saying his big breakthroughs, they started earlier. He was challenging the status quo, the old ideas.
Oh, absolutely. Long before the telescope became his famous tool, he was going up against his whole established hierarchy, mostly Aristotelian ideas that sort of kept motion locked in abstract thought, not real-world observation.
And Aristotle's view was things don't move unless you push them, basically.
Pretty much. A state of rest was natural. Motion needed a constant cause. But Galileo, he did something different. He decided to let motion do the talking.
How? What does that mean in practice?
Well, he picked things up. He used inclined planes. He watched pendulums swing. And later, yes, the telescope. He wasn't just theorizing. He was experimenting. He was, as our sources put it, listening to structured motion resolve itself through experiment.
So setting up conditions, watching carefully, repeating it.
Exactly. Watching motion under constraint over and over until the loop revealed its pattern. It's this incredibly patient empirical approach. And that, as we'll see, really laid the foundation for this motion theory idea. It's like he was turning into the universe's own frequency.
It's a huge shift from just philosophical debate, isn't it?
Massive. Letting the physical world, the phenomena, guide the understanding. It sounds obvious now, maybe, but it was radical then.
Okay, so speaking of tuning in, his first big insight, the sources say, wasn't the telescope, it was a lamp in a cathedral. That sounds almost too simple.
It does, but it's apparently true. He's watching this lamp swing, probably during a long service.
Yeah.
And he notices something amazing.
What was it?
That no matter how wide the swing arc was or how narrow, the time it took for the lamp to complete one full swing back and forth, it stayed the same. Consistent.
Okay. Isochronism. Equal time.
That's the one. Isochronism, equal time motion loops. And that's a huge aha moment.
Yeah, and for motion theory, that's like a perfect example, a harmonic loop. Motion finding a rhythm under gravity.
Precisely. It's motion resolving across a fixed rhythm because of a constraint, in this case, gravity and the length of the chain. It's all about that predictable repeating pattern.
And he didn't invent the pendulum, obviously.
No. But he felt its rhythm, as one source says. He realized this consistent beat could be used to measure other things, to measure motion by motion.
An internal sync clock.
Kinda, yeah. Using one loop's reliable rhythm to track another's, he's starting to see the universe as these interconnected, measurable rhythms, building the architecture for motion theory without even naming it.
Wow. Okay, so from the lamp's rhythm, he moves to the inclined plane, which is basically a ramp, right? Why was that so important?
Well, gravity is fast. Things fall quickly. Hard to measure accurately back then.
Yeah.
His genius was realizing that rolling a ball down a gentle slope was like watching gravity in slow motion.
Clever, diluting the effect of gravity.
Exactly. It allowed him to take measurements. And by doing that, rolling balls down these planes, he found two massive things.
Which were?
First, that falling objects don't just fall at a steady speed, they accelerate. And they accelerate uniformly, consistently.
Okay. And second?
Second, he figured out the relationship. The distance the object covers increases with the square of the time it's been falling. D is proportional to t squared.
Right, the famous equation. And this just completely blew up Aristotle's idea, the whole heavier things fall faster thing.
Completely shattered it. Galileo showed, or at least strongly argued, based on his experiments and thought experiments, that weight didn't matter. Air resistance might, but fundamentally, gravity affects all objects the same way.
In motion theory terms, then, all objects, or all motion loops, they resolve that gravitational pull the same way, by speeding up.
Yeah, by increasing rhythm to stabilize, as the sources frame it. It's a universal principle he was tapping into.
Now, the sources connect this to a different view of gravity in motion theory, not just a pull, but convergence towards denser synchronization zones. Can you unpack that a bit? That sounds pretty abstract.
It is a bit, yeah. Think of it less like a force pulling things down and more like, well, imagine a tightly packed group of dancers moving in perfect sync. That's your denser synchronization zone, like a planet or a star.
Okay.
Objects nearby, which are also in motion, naturally tend to adjust their own rhythm to match the dominant rhythm of that denser zone. They fall into sync.
So falling isn't being pulled, it's like being drawn into the main beat, getting into rhythm.
That's the idea. Especially when undisturbed, they sync up more rapidly. That natural tendency for motion to harmonize, to stabilize, to increase its rhythm as it approaches that sync target, that's the dynamic resolution logic. It's about motion finding its place in the larger rhythmic structure.
Okay. That's a different way to think about it. And then he gets the telescope and turns it upwards.
It boom.
Yeah.
Shatters the old cosmology. The perfect unchanging heavens idea. Gone.
What were the killer observations?
Oh, several. He saw moons orbiting Jupiter. Moons, not orbiting Earth. That was huge proof positive not everything revolved around us.
Right. A direct challenge to the geocentric model.
Definitely. Then he saw mountains and craters on the moon. The moon wasn't a perfect, smooth, celestial sphere like Aristotle said. It was imperfect, rugged, like Earth.
Blurring the line between the terrestrial and the celestial.
Exactly. And then the phases of Venus. Seeing Venus go through phases just like our moon that only made sense if Venus orbited the sun, not the Earth. Direct evidence for Copernicus.
So putting it all together, the universe wasn't static, it wasn't perfect.
It was in motion. Constantly. And it wasn't divinely perfect in the old sense, but maybe rhythmically evolving. A dynamic system.
And the motion theory angle sees this as nested synchronization loops.
Yeah. Planets orbiting stars, moons orbiting planets, stars moving within galaxies. It's all loops within loops within loops, all orbiting, rotating, resolving tensions on different scales, but all interconnected rhythmically.
So Galileo wasn't just observing, he was syncing up.
He phase-locked with celestial motion, is the phrase used. He tuned into those cosmic rhythms, and, crucially, he let others see the sync for themselves through his telescope. He showed humanity the cosmic dance.
Incredible. Okay, let's shift gears slightly. Inertia. This feels like another huge conceptual leap. Getting rid of the idea of a natural state of rest.
Oh, absolutely fundamental. Aristotle's view dominated for centuries. Things stop unless you keep pushing them. Rest is default.
But Galileo said,
through brilliant thought experiments, imagining perfectly smooth surfaces with no friction and his real experiments, he basically concluded an object in motion stays in motion at a constant velocity unless something interferes, like friction or air resistance.
Wow. So the implication is?
Motion isn't temporary. Motion is the default. Rest is just one possibility, maybe even a special case, that just flips everything on its head.
It really does. And motion theory calls this loop momentum.
Right. A rhythm, state of motion, that just continues unless some external sync pressure, some interaction, forces it to change or redirect.
So what we call rest
is just a temporary sync condition. An object at rest on Earth is just synchronized with the Earth's motion, temporarily stable within that specific rhythmic context. It's not the absence of motion, it's a particular kind of synchronized motion.
Okay, that reframes things completely.
Yeah.
So digging into how he did all this, it wasn't just having good ideas or good eyes, it was his method.
His method was revolutionary. It wasn't just what he saw, but how he observed, how he tested.
He repeated things. Right. Changed one thing at a time.
Yes. He repeated experiments, isolated variables, and crucially, he let motion prove itself. He set up these looping trials, as the sources call them.
Looping trials.
Yeah, like each run of rolling a ball down the ramp was a test of the system's rhythm, a sync test. And the outcome, the measurement, was the phase resolution. It showed how the motion reliably resolved itself under those specific constraints.
That sounds exactly like the motion theory description. Create a loop. Adjust the tension, observe the rhythm, repeat until the structure stabilizes.
It really is. It's like he was performing motion theory in practice centuries before anyone used that label, using motion recursively to understand motion itself.
And that iterative process, that's the core of science now, isn't it?
Absolutely. Building reliable knowledge through repeated controlled observation and testing.
So, looking at his legacy, obviously huge influence on Newton, classical physics.
Undeniable.
Yeah.
Newton built directly on Galileo's work on motion and inertia.
But the sources suggest something deeper than just the formulas, a way of thinking.
Yeah, it's about the questions he asked. He fundamentally shifted the focus. Instead of asking the old question, what causes motion, he started asking, essentially, what does motion do? What does motion want to resolve into?
From cause to resolution.
Exactly. And that's the core question motion theory keeps asking today, right? What's the loop? What's the constraint, the tension? And what's the sync target, the stable rhythm it's trying to achieve?
So summing up Galileo, motion decoder seems pretty spot on.
I think so. He took the mystery out of motion, in a way. Showed it wasn't some mystical force, but something understandable, measurable, rhythmic. He removed the old hierarchies from the cosmos.
He listened to pendulums, falling bodies, planets.
He let them speak. And by doing that, he triggered a sync cascade in human thinking, a chain reaction of understanding.
Motion theory doesn't claim he was perfect, but that he was onto the rhythm aspect way early.
Yeah, he was right about rhythm before rhythm had a name. He stopped listening only to ancient philosophers and started listening, really listening, to motion itself. It was always there. It was always motion.
What a mind. Okay, so wrapping up, we've gone from cathedral lamps to Jupiter's moons and seen how Galileo revealed this universe of interconnected rhythms and resolutions.
And that key shift in perspective, not just what causes it, but where is it going? What stable state is it seeking?
Yeah. And that leads to the final thought for you, the listener. We want to leave you with something provocative.
If Galileo taught us to look for these inherent rhythms, these natural resolutions in physics,
Yeah.
how could you maybe apply that mindset elsewhere?
Right, in challenges you face, maybe in work or life, instead of only asking what caused this problem or how do I force a solution?
Maybe also ask, what's the underlying loop here? What are the real constraints? What does this situation, this system, naturally seem to want to resolve into?
Try observing those loops, the constraints, the potential sync targets in your own world.
You might find, like Galileo, that it leads to a deeper understanding of the patterns and maybe points towards more natural, stable resolutions. Something to think about.
Definitely. Until next time, keep deep diving.